Now let's come back to another matrix operation, which is rank determination operation, which is also very, very useful concept. The rank is essentially the number of dimension in the output of a transformation. So if I take a vector and if I multiply that by a matrix, you understand geometrically that that will transform and become another vector. The question is whether the transformed vector, what is the actual number or the minimum number of dimensions that are required to represent that vector. If that is equal to the original dimension of the vector which resulted in that transformation, then it's full rank, right? And that concept is essentially associated with the rank. Okay. Now, if I take a three-dimensional vector and multiply that by a matrix, and only two dimensions are needed, the transformed vector can be represented only by two, then the rank of that matrix is going to be 2, not 3. And that is the concept associated with ranks, and this is something that we need to understand, which is essentially the idea that after transformation, what is the minimum number of dimensions that is required to represent the transformed vector, and that determines the rank of the matrix itself. Okay, and so this is denoted by this rank, round parenthesis m, and if the rank output of any transformation, so let's say if you have n-dimensional vector or three-dimensional vector, and after transformation it becomes a line, and we only need one unit vector, which is I, to represent it, and j and the kth component of that vectors are 0, we essentially need only one unit vector, right? So in that case, the rank of that matrix is going to be 1. Whereas, let's say if you take a three-dimensional vector and we transform that, and after transformation, we only needed two unit vectors I and j, whereas the third component, kth component, became 0, and we did not need the third component to represent that vector. In that case, we will have a matrix whose rank is 2. Okay, as the number of dimension is 2. Okay. So here are other ways to understand it. For example, a 2 by 2 matrix after transformation, if it spans the full 2D space, something like this, right? Then we have essentially the output dimension equal to 2, because we still, after transformation, we need these transformed unit vectors. We need we need 2 unit vectors even in the transformed space, right? So if that's the case, we have a matrix which is a two-dimensional whose rank is 2. Now let's take and determinant is non-zero. Now take another example where we have this 2 unit vector in the original dimension, and when we transform this unit vectors using the matrix, and in that case either they form in a line opposite or maybe along the same direction, we only need one unit vector to represent that. And in that case, geometrically we will essentially have the matrix to have the rank 1, or the output dimension of that matrix is going to be 1, and this is the concept associated with the rank, right? Where we want to know, how many unit vectors are needed to actually represent the transformed output of a given matrix. And in this case, you will turn out that the determinant is going to be 0, and this could be used as an idea to determine the rank of a given matrix. Okay, so let's take some numerical examples to understand this concept. Geometrically, we discuss what the idea behind rank is. Let's take numerical examples and see how do we do the rank computations. So in order to do rank computations, it is mainly involved with the determinant aspect of it. So let's say we have a matrix M, right? This is a matrix M, and if we want to determine the rank of this matrix, what we are going to do, the order of this matrix or the number of elements is going to be 3 cross 3. So we know that the rank could be anything less than or equal to 3. So it could be full rank, in which case the rank is going to be 3, or it could be 2, 1, and so on. Okay, so the order is going to be there. So in order to determine the actual rank, what you need to do, first you consider the third order minor, which means you consider the whole matrix and you determine a determinant. So you take this, you take the third order of matrix, so this becomes a determinant of this one, and you calculate the determinant of this. This came out to be minus 62, which is not equal to 0. So since the determinant is non-zero, that means this matrix is full rank. Okay, and if you use it for transforming purposes, right, we will not lose any of the dimensions. So in this case, just by testing the third order minor, determinant of the third order minor itself, we know that this is full rank, and the rank of this matrix is going to be equal to 3. Okay, so that's the one example. So rank of this, at least for this example, is going to be 3. Now let's take another example, right? This example 2, where we have this matrix B, which is given by these elements that are here. Okay. Now again, this is 3 by 3, so the maximum rank could be 3 or it could be less than 3 also. So how do we go about finding out the actual rank? The first thing, we begin with the highest order, minor. So this is 3 by 3, so we will start with the third order minor. So we will take the whole matrix, we will determine the determinant of the whole matrix. It turns out if I compute this matrix determinant, it became 0. Now the determinant of the third order minor of this B is 0, so that means the rank of this matrix is not 3, it's less than 3. Now we will go ahead and dig deeper and consider the second order minor. So let's pick any second order minor, and what we have picked is basically 3, 0 and 2, 4. So what we did is basically we eliminated this row and this column, and we considered one of the second order minor of the matrix B. Okay, so we did this, we took the determinant of the second order minor, okay, which is 3 minus multiplied by minus 4 minus 2 times 0, which is equal to minus 12, and this is non-zero. So if any of the second order minor of this matrix is non-zero, then that determines the rank of it. So in this case, the second order minor, right, is non-zero, so this rank will be equal to 2. If this was 0 and all the other minors were all of them is 0, then we need to go to the first order minor and see if all the elements are 0 or non-zero and so on, right? So that's the process of determining the rank, numerically determining the rank of a given matrix. So again, here the determinant is non-zero for our order 2 matrix, a sub 2 matrix that we have. So in this case, essentially the rank is going to be 2. Why? Because the third order minor, determinant of the third order minor was 0. So we dig down deeper, but the second order minor we had a non-zero minor, and that's why the rank of this matrix is going to be equal to 2. So with that, thank you, and we will come back with the next set of lectures where we will be also discussing some other important concept.